How's that look? Is that visible? Let me switch the lights down. Better? Last lecture, I tried to motivate machine learning, in particular by looking at an example, a historical example of predicting an orbit by Gauss, which I sort of said was, roughly speaking, mostly a deterministic prediction. That's not quite true because there's some stochasticity in terms of experimental error, and we mentioned that a little bit. And then we talked about how you might try and predict the position of a molecule of air, and how that's completely stochastic. And I sort of said, well, machine learning is often trying to look at things that are a combination of stochastic and deterministic. So somewhere in between. And what I actually wrote down on the board was a simple linear equation where I said, okay, if you have y is equal to mx plus c plus noise, where that piece is the deterministic part and that piece is the stochastic part. And this is what we're explicitly modeling, and this is the corruption the rest of the world is putting in place. Okay? So I hope you all read the section from Bishop on probability review. It's material you should know before doing this course. Did everyone get a chance to look at that? I think there's reference text in the library. I also was looking at this text. This is a new text, and I think this is actually by a friend and colleague. So, Mark Rogers. Mark, let me. I think there's probably some, this text here, which I just got through. I ordered it in preparation for the course. It's a bit yellowy, isn't it? Maybe the plugs are. I ordered it in preparation for the course, and I just got it through yesterday. And I had a flick through, and I think, I know Mark and Simon quite well, and they think the same sort of things about machine learning, and the material they cover looks similar to the sort of material I intend to cover. So we haven't said that this is the set text because it only was released last year, and we based the course mainly on Bishop. But I think it's worth checking in the library. There may also only be one copy, if any, but that's one worth looking at as well. We may try and integrate that a bit more as the course goes on. I also spoke to John Barker a bit about who here's in the 4th year for computer science? So you guys all did this 2nd year course, which I think was run for the first time, which covered some of the material that would be introduction to this. Now that could be just a practice, or it could be a genuine, like they like to do at the start of term, make us all go and... Have you had one already?
But it wasn't in a drill, it was a course alone.
Oh, there we go. Okay, good. We don't have to go and stand outside. Good. Oh. Okay. So, talking to John about some of the things he taught, they're related. And I did start to worry. When I studied French at school, I think I started taking French from the age of 9. And what seemed to me is they just used to teach the same thing every year. And you do that until the age of 16 and get tested on it. So I hope that's not going to happen for those of you who've done that course, because what we're trying to do is be much more detailed about those type of ideas. But you've all seen some of those concepts before. So what do I want to do today is pick up from that section on Bishop, which was really talking about probabilities in terms of a fixed number of discrete events and a table of numbers. So for example here we have x, and x has 3 possible outcomes. It could be 0, 1 or 2. And the probability of each outcome is given by a set of numbers. So x may be some event we're interested in. It might be the probability, the age of a young baby. And we can look at the baby, we know it can't be 3. We think it must be about 1. but it could be younger because we're not that used to seeing babies, or it could be older. Something like that. It's representing our belief about the state of the world. Now, that's fine, and in fact, Laplace did a lot of work on probabilities like this in the context of gambling, where you've got dice. And all the early work on probabilities was done in gambling. In fact, there's a famous book by de Moivre, who was a Frenchman, but I think he was an Huguenot, a Protestant Frenchman, so he moved to Britain. And in the introduction to his text, it's a treatise on probabilities or something. He specifically writes, look, I know that probabilities are really about gambling, and that's completely immoral, but it doesn't mean this area of maths is immoral. So that was the main motivation for studying probabilities. And Laplace looked at things like, if you've got a coin where you would have a probability of heads or tails, trying to infer that the probability of the coin is biased. So the French would call a dice, if it was biased, they'd call it an English dice. We called it a French dice if it was biased. But he talks about, how do you tell if a dice is English? And then he looks at the simpler situation of a coin. How do you tell if it's a biased coin? And looks, so that this is going back to sort of late 18th century. But what we're going to be interested in, certainly in the first part, so this is sort of a histogram representation of that distribution. But what we're going to be more interested in is the situation where you have I haven't gone to that in a bit. No, just a couple of review things about the discrete distribution. So what these probabilities tell us is the distribution over some number of states we're interested in. So, but we might be interested in a function of those states. So you might be interested in a function of those states. For example, that function could be, if you guess the baby's age correctly, you get £100. Yeah? Something like that. So that's a function of the state. So it means that if the baby's age is 1 and you guess it's 1, you get £100. So that's an f of x. It could be various functions of the state, but what we're interested in is how the probabilities relate to those functions. And what we use there, and you should have seen this before, is expectations. So an expectation is the sum over all the states in the probability distribution the probability times that function value. So a simple expectation is known as the mean, just the function being f of x is equal to x. And to compute the mean of this distribution, you need to take the function, which is x, times the probability and sum them all up. So 0.2 times 0 plus 0.5 times 1 plus 0.3 times 2. So that would be the first moment, or the mean of the distribution. So on that plot I showed earlier, that's where that mean is. Now notice in the discrete distribution, the mean will not be something, typically, that you can sample from the distribution. So while it's supposedly characteristic of the distribution, it has 0 probability. Because this can only be 0, 1 or 2, and the mean was 1.1. But 1.1 can't come from the distribution. Because it's a characterization of what over time the average, because it's x, the average of just these states would be if you sample from this distribution. So the average can be 1.1, but none of those individual values can be 1.1. So similarly, and this should be review, it's in Bishop as well, but beyond the section I talked about, so I've set reading this section for after this lecture. We can compute what's called the second moment of the distribution. That's the square of x. So if we're looking at the square of the x, so here I've shown the square of x, 0, 2, 4, and to compute the second moment, again, the same trick. 0.2 times 0 plus 0.5 times 2 plus 0.3 times 4 is equal to 2.2. Now the second moment's important because it's then used in computing the variance of the distribution. And the variance of the distribution is that second moment minus the first moment squared. Now, if you think about that, yes?
If the square computed, is it 1 1 to the power of 2?
It's the square of x, so x is 0, so 0 squared is 0.
But how much is 1 squared? 2 is 1.
Yeah, that's true. Yeah, sorry, that should be 1. Gee, that's a good error, isn't it? How embarrassing. Yes. Okay, thanks for that. Yes. So that should be, so that's a miscomputation. And in fact, that explains, I was looking at this slide thinking that's funny, but I didn't double check. That explains why the variance is too wide, doesn't it? Yeah. Very good. We'll cut that out of the recording. So yeah, quite right. Some silly error by me. That should be 1, and 0.5 times 1 in here. So this would be 1.2. Sorry, 1.7, yes. And this would be 1.7 times minus 1.1 times 1.1, which is going to be about 0.49? 49 or something like that? Yeah, so it's 0.5 less. And, okay, sorry, apologies for that error. So the variance is formulaically correct. There's an error in here. So it should be smaller than that. And we'll see that on the next plot, actually. The variance shows you the tendency of the distribution to fluctuate around the mean. So the nice thing you can see about this formula is if all the probability was located on this 1 here, so it was 1 here, and 0 and 0, the variance would actually be 0. Yeah? As you distribute the probability across the distribution, it reflects the width of the distribution. And what we tend to plot is the standard deviation, because that's in the right scale. This isn't a squared of x scale, and this is... So we have an error on the next slide, which I did spot, and I should have gone back. You only reminded me of it. I should have gone back and followed it through. So that variance should be much smaller. It should be in there. That's way too large, right? That should be in there like that. Okay. So that's the sort of moments, the first two moments, and particularly the variance. But what I want to push into quickly, because what we're going to look at in the first part of the course is continuous variables, not discrete. And in continuous variables, we're interested in probability density functions. So, you are not allowed to ask a question in a continuous space. What's the probability that this person's height is 6 foot? Why are you not allowed to ask that question? Well, you can ask it, and I can tell you what the answer is.
Because it's an infinitely small range.
Yeah. So the probability is 0. You know, it might be about 6 foot, but the probability anyone's height is exactly 6 foot. Exactly 6 foot is 0 in a continuous space. If we discretize heights into 5 foot, 6 foot, 7 foot, then the probability can mean something. So probabilities on discrete ranges can mean something. On a continuous range, the probability is meaningless. Yeah? And that's very important to remember, but there's a trick. So you can only ask a question about a discrete interval. So you can ask a question, what's the probability someone's height is between, let's use meters, 1 meter 95 and 2 meters 5. Yeah? That's a range. So there's two probabilities there. There's a probability that you're in that range and a probability you're not in that range. That's a well-defined discrete question. Now what a probability density function does is it actually allows, it's a function that allows you to answer any of those questions you might imagine. Yeah? So it's just a trick. I mean, it's an important point, but once you've understood the point, you can actually forget about it because you just use probability density functions as you use regular probabilities, but you mustn't forget they're not a probability. So here's a probability density function, and what it is a function which is always positive, which integrates to 1. Yeah? Now that integration to 1 means that if I take any range of this function and I say, okay, what's the integral of this function within this range? That's less than 1. Yeah? And because the whole thing integrates to 1, the complement of that, this bit outside, is 1 minus that. So you can ask that question, a discrete question about that probability function. And any question you can think of about any discrete range can be asked. We can ask, what's the probability you're less than 6 foot? Or what's the probability that you're, greater than 6'5"? Yeah? We can ask all those questions. Importantly though, I just asked those questions in feet. What happens if I ask those questions in centimeters? Well, the same, yeah, I get the same answer if I use the discrete intervals. But what happens to this function is I change the scale on this axis enormously. And so the height of this function actually moves dramatically because it must integrate to 1. Now you see how it's an example of why it makes no sense to ask a question about a height, an individual height. Because if I rescale that axis to keep the integral of this to be 1, so if I move it onto centimeters, so that this axis is now going up to 205 instead of 6.5, yeah? That, to keep the integral the same, the height of that has to drop. So the value of the function is entirely dependent on units. Not even just units, we could actually make a nonlinear transformation of this probability density function. So instead of height, we could talk about logarithm of height. And we could plot this function. It would then look different. Whoops. It would then look different. It might look something like that, yeah? Now, this function would then be a completely different shape. But importantly, if we ask about any range in that function, the logarithm of that range would move to the new logarithm of the range. The area would be the same. So that's the thing to remember about probability density functions, that when you ask for the probability of an individual point, it's absolutely meaningless because I can change the scale and that moves. Yeah? You can only ask about the probability between 2 points. So for example, if you measure height in units of 10 meters, which is an odd thing to do, but one effect would be, so this is 1 unit of 10 meters, so you're down here in about 0.2 units of 10 meters would be where your distribution was. So in order for it to integrate to 1, it would have to come up to about 5 in height. So the value of this function could be greater than 1, yeah? But the probability of any interval will always be smaller. So that's an important point. But the interesting thing about these probability density functions is once you accept that point, you can just move on. And you can treat them always as if they're probability. Not always, that's a lie. You can treat them a lot of the time like they're probability distributions. So the sum rule that you should have been looking at in Bishop, the product rule, Bayes' rule, all work for probability density functions. Yeah? But it's a functional representation. So we're going to use the word distribution to refer to, I think that you should use a separate word, but very often people don't. But we're going to use the word distribution to refer both to discrete probabilities and density functions of the type I just showed. Okay. I've lost that as well. There's another error. That's not going to make much sense, is it? Okay, so that's supposed to be Bayes' rule that you've studied. And expectations, this one does work at least. That was a change of notation that I didn't follow through on, sorry. Expectations are the same as well, but they're replaced by integrals. So wherever you get sums with probabilities, you get integrals. This should be P of y given x is equal to P of x given y, P of y over P of x. But just Bayes' rule for that you should have seen in Bishop in the probability review. Now, perhaps the most common, and to some people, the most uninteresting probability density function is the Gaussian density. And we're going to make extensive use of it. I want to teach you to love this distribution. I used to hate this distribution because I associate it with statistics classes where I had to compute means and look up you used to have to look up tables of normal distributions to compute the probability of where you were falling in the distribution. It's the distribution that we saw last time that Maxwell derived as the distribution of molecules in the air, their velocities. And importantly, it's also available in a multivariate form. And that's where it gets really interesting. But for the moment, we're just going to look at the univariate form. So it's parameterized in a particular way. Over the years, this parameterization has evolved. It used to be written in a couple of different ways. It's got this mu, which is what we call a location parameter, and sigma, which is a variance or standard deviation parameter, or even you can think of it as a scale parameter. Now, whenever you see a probability density in this form, you can think this argument here that's squared is x minus mu over sigma over 2 sigma squared. But pull the half out. X minus mu over sigma all squared. Yeah? So the operation you can see that mu and sigma are applying are a scaling and a location. Yeah? So you can take, if you think of the standard normal, what we call the standard normal is that with 0 mean and unit variance. It sits at 0 like this, and the standard deviation turns out to be 1 if sigma's 1. This is sigma equal 1, so sigma squared also equal to 1. Thanks for pointing that out before. Mu is equal to 0. If we change mu, we change the location. So if we make mu 3, because it's minus mu, the location of the distribution moves to here, or the density moves to here. And if we change sigma, we change the scale. So we can flatten it out, and we can make it go peaky. In the limit as sigma goes to 0, it becomes what we call a delta function. So it becomes 0 width and infinite height because of the sigma at the front. This is the normalizer, and there's an exercise in Bishop that describes how to try and compute that normalizer. I'm not going to, I think it's exercise 1.2, I'm not going to examine you on that, but it's worth looking at. It's non-trivial actually. So it's a density that was first proposed by this fellow de Moivre in his book where he apologized that probabilities were about gambling. And he was proposing it because it turns out that it's an approximation to the binomial density, which is something you haven't seen in this course, but you may have seen before, which is the result of lots of summing, lots of coin tosses. But it was also used by Laplace, and Laplace importantly used it to do something called Bayesian inference. He wasn't aware of de Moivre's use of it, he invented it independently afterwards, but he was using it actually for Bayesian inference, which is something we're going to cover. Not the way he did it, but yeah, so here it is. There's a drawing of it, and here I've used it to represent heights. Why might it not be a sensible density to represent heights? There's an objection to why I'm using it for representing heights.
It's because people can it varies with age as well.
Yeah, but we could accommodate that. That's not the reason I'm thinking of. It's actually a fundamental reason. It's not quite obvious in this picture because of the way I've set it up. But think of this picture. This is 0, this is positive, this is 0, this is negative.
Can't have a negative height.
Yeah. Who said that? Oh yeah, very good. So none of you have a negative height. Okay? Now interestingly, the normal distribution here, I've drawn it in such a way that the probability of a negative height is infinitesimally small. Sampling from this density, you would never see a negative height in the history of the entire universe, even if you sample every nanosecond, because these tails fall off very quickly. Yeah? But in theory, it has got support here. There is some non-zero probability for negative height, which shows you there's potentially something wrong. So that's one thing you have to think about when you're using densities. Is it the right density for the purpose? It doesn't mean you absolutely shouldn't use it, but sometimes if you use it, you have to be aware something can go wrong. And this happens for us, for example. One thing we use Gaussians, we try and use something called a Gaussian process for, that I'm going to tell you about a little bit right at the end of the course, is modeling the functional form of a probability density, like a general probability density. People try and use it for that. But the difficulty is it allows the probability density to go negative, which is obviously can never happen. And that does cause problems. People work hard to resolve that. So yeah, I've used it here for heights, and it is probably very reasonable. But be aware, in practice, you shouldn't use it for things that go positive only. So the PDF doesn't represent those probabilities directly, and damn it, it's the same. I've got this nice ability to change my notation throughout the slides, which I cleverly did at the last minute, messing up all the slides. So what's the probability that x is less than y, some value y? So this is supposed to say, let me just rewrite that equation on the board. I was trying to match Bishop's notation better because I noticed I had a mismatch with Bishop's notation, and that's what's caused the problem. Okay, so you might want to ask the question, as we've asked before, what's the probability that a height is greater than some value? Yeah? And what you need to do is be able to integrate from, well, if it's asking for less than that value, you need to be able to integrate from minus infinity to some value z, that probability distribution. So this gives me the probability that from minus infinity to z, it gives me the value of the function under there. So it gives me the probability that something is less than z. I can then use that cumulative density by saying, oh, here's the probability that it's less than z, here's the probability that it's less than z2, and I can then get the probability that's between z2 and z, yeah? So the cumulative density function is very important, and it is actually a distribution. It's always between 0 and 1. And here it is for the Gaussian. It's actually called the cumulative Gaussian, but it's represented by something called the error function Earth, yeah? So when they derived what this integral was, there was no functional form that already existed, so they had to invent a new one, and that's called the error function. You used to have to look it up in tables, but it's available in MATLAB and Python and R just for you to compute. So as you go through the density, the probability that it's less than 1 is sort of 0 pretty much, close to 0, it won't be quite 0, but then the probability it's less than 1.5 is some non-trivial value until the probability that it's less than about 2.25 is 1. Yeah? Makes sense, doesn't it? So importantly, these cumulative density functions are monotonic. Because this function is always positive, this can't go up and then drop down. Yeah? It always has to keep going up. It can plateau like this, but it can't drop down again. So that's a constraint for something to be a cumulative density function. It must be between 0 and 1 and must be monotonic. Because the CDF is the integral of the PDF, you can recover the PDF from the CDF through differentiation. Yeah? Simple relation between them. Okay. Now another thing, in practice, you don't know the distribution that you're interested in. What you really, the way we're trying to use probabilities, okay, there are cases where you know it. So Maxwell could, under certain assumptions about a gas under low pressure and inelastic collisions and circular balls, he could derive a Gaussian density for being the distribution of molecules. And it comes from simple assumptions that are going to be correct under those circumstances. That's a rare occasion when you have a pretty good idea of the truth of the probability distribution. But even then, if you put that gas under very high pressure, it won't behave like that. If you change the molecules in the gas so that they interact more, it won't behave like that. And the distribution becomes wrong. The density of velocities becomes wrong. So in practice, you don't know the distribution that the world's generating data from. Yeah? So somehow, you all have heights, and that is some complex result of who your parents chose to marry, what their genetics were, what you ate as children. I mean, a lot of height is thought to be epigenomics, what your environmental conditions were, whether you've just got out of bed or not, because apparently you grow a little bit at night. So it's a very complicated density, right? And we don't know all the details of it. But what we can do is we can use so-called sample-based approximations to expectations. So if we observe a bunch of student heights and we're saying, well, your heights are sampled from this generic student distribution, that's a reasonable assumption, we can replace the actual expectation with a sum over those observations. So if it's f of x we're interested in, we take each observation of height. So if we're interested in your height squared, we square it, and 1 squared is 1, be careful with that. We square all those heights and add them all up, and then divide by n. That gives us an estimate. It gives us an estimate because of the law of large numbers. Yeah? The law of large numbers says that this is true. It's one of the fundamental theorems of sort of probability, that as you increase n, under certain conditions on P of x, which we're not going to worry about, it's about whether this sum will converge under P of x. It's an interesting thing, actually, but I don't want to worry too much about it. That this sum will converge to that value. How quickly it converges is dependent on various properties of P of x, but that's the idea, it's going to converge. Now that leads to a particular confusion, I think. that when you talk about the mean of something, what do you think the mean is? Most people, I think that that's a mean, yeah? And it is a mean of a type. The sum of the observed values divided by n, yeah? That's an average. But it's only the mean because it's the sample-based mean. I think that, personally, I mean, this is my way of thinking about it, to differentiate between, not differentiate mathematically, but to make these things different. In my head, I think of that as the sample mean, and it's an approximation to the true mean that I don't actually know. Yeah? So people use that, they say, oh, let's compute the mean of the data. But in some sense, I like to think personally, I'm not saying everyone thinks like this, that the real mean is associated with this distribution that we don't know. And all we can compute is an approximation to it that would tend towards that true mean, the true population mean across all possible student heights if we were to get all the students generating mechanisms done. So that tends to be the way I think of it. And this is, you know, this was my most hated thing at school, because when we were taught statistics, it seemed to me that computing that was all we did. Yeah. But that's not what probability is about, really. So it's the same for discrete and continuous PDFs. The key point is that these samples, for this to work, need to be obtained independently from this density. And the approximation gets better for increasing n and worse if the samples from P of x are not independent. If they're correlated for some reason, then it becomes quite bad. So I think we'll just skip through that. Okay, here this one is right, at least on the x squared. What I want to do is focus on this last question here. This is something, it's like an exercise in Bishop as well. I think you can go through that in your own time, but for the purpose of the next lecture, I want to just discuss this particular quantity, because you'll read about this also in Bishop, and it's a very important thing. It's associated with the information content, and it leads to something that we call the entropy. So the expected value of the log of the distribution. Now, as you'll see in I'm going to introduce maximum likelihood in the next lecture, and I'm going to introduce it through an information theoretic quantity. We're not going to do too much on information theory, but why the log? So Bishop has this justification of why if I can recall it properly, which I may not be able to. If you've got two independent events, so independent events, the joint distribution is the product of the marginal distributions, yeah? Like this. So Shannon, in the 40s, developed a theory of information, which was really about understanding communication and how much information you could push down a channel, yeah? It's core to computer science. We use it a lot. One of the conditions he said for that is that information should be additive. So that if I find something out about x, and I find something about y, and x and y are two completely independent things, then what I find about y should add to my information about x. The knowledge I should have should be additive. So that motivates a logarithm, yeah? Log p of x times p of y is, log p of x times p of y is equal to log p of x plus p of y. In fact, that's unique. That's the unique definition of log. If you say that you want a function such that f of x y is equal to f of x plus f of y, the only function that can do that is logarithm. Yeah?
Sorry, you lost me a bit. If x and y are completely different, then why should the information be additive?
Because, so you're trying to, if you mean if x and y are two different things. Because so let's say x and y are your height and your weight. then the idea is if I'm communicating information about your height and I'm communicating information, they're not independent actually, so it's a bad example. But if they were independent, if I was communicating, once I learn something about your height, and then I independently learn something about your weight, I've got two things I'm learning that I want to communicate. Does that make sense?
But there must be something that connects them, like the same subject.
Normally, not necessarily. So that's the point. There would be for height and weight. So the point about the theory and why independence is needed for that is if there's a relation between them. So for example, if everyone had exactly the same body mass index, then if they gave me their height, I would know their weight. So there's no information gained. Once you know their height, the information gained by knowing their weight is 0. Yeah, so as things become related, the amount of information you gain by knowing multiple things becomes less. This is, I mean, we're not doing a course on information theory, but that's the idea behind information theory. If we're trying to identify, we're trying to identify people in this room, we get more information about you if we learn independent things about you. So if we learn, I'm now trying to think of something that's completely independent of each other, which is quite hard. Hair length, yeah. So if we wanted to identify, that's a good one. So hair length, well, I don't know, might be dependent on height. People might think, oh, I'm tall, I need longer hair. Yeah, no. and women have longer hair and they're typically shorter. But okay, let's assume hair length is independent of height. So if I wanted to identify people in this room, there's a distribution of hair length, there's a distribution of height. So the first thing you say to me is, I'm standing facing the wall and I know all information about all of you, right? And then you say, well, the height is between 6 foot and 6 foot 1 inch, because you're not allowed to say it's exactly something, because that wouldn't make sense. Okay, that might narrow down the field to 5 of you. And then if independently you then say, and the hair length is this, then that actually gives me more information about who, even though it's independent, I get more information about who the person we're talking about is, yeah? Does that make sense?
Yes. So what's P of X and Y then?
So that would be probability of height, that would be probability of hair length.
The one underneath.
This one here, that would be the joint distribution. So height and weight are related. So, and I use that as an example for a multivariate Gaussian later. So if height and weight are related, then if you plot height versus weight, they live in some density like that, so with some correlation. So if P of X, comma Y is independent, you can write it as that. In which case you don't get this correlation, you'd see some density which had no correlation, yeah? That it would just be two separate things. We'll go through that when we go through multivariate Gaussians a bit more. So if they're independent, then the information becomes the log of one plus the log of other. So it's important for information content, the log of P of X. Okay, so that's another example that you can also go through. So I wanted to spend sort of extra time talking about the maximum likelihood bit that follows this, but these are the bits I'd like you to look at in Bishop, which discuss these concepts. So probability densities in section 1.2.1. That's, I think, the remainder of, I think I asked you to read up to 17 before. Expectations and covariances, yeah? So we've looked at them briefly, pages 19 to 20. This should all really be review. But I want you to understand it fully because I want you to refresh your minds on it because it's fundamental to everything else we do, yeah? So it's good questions like yours are good because, I mean, my experience, I hated statistics at university and at school, and I avoided all the courses that had anything to do with them. I did like things on differential equations because I was an engineer, because I didn't see the point of this stuff. And so I never really got an intuition in it until I started thinking about it in my PhD, till I understood, oh, actually my PhD turned out to be about probabilities. And now I really love them. But I didn't like the way they were taught or the way they were thought about. So, I think you need to go in and read these things. You may be similar to me that you didn't care about these things before, but hopefully you will care about these things after this module. Okay. Right, so that's the first section, and I'm going a little bit fast through that because I actually wanted to spend more time on the maximum likelihood. So what we can do first is we can either take a break now and come back a little bit early and go for an hour and 10,